get started? You're still okay with me not using the microphone, right? Okay. As long as people in the back are hearing me fine, we should be okay. Okay, we'll continue the use of emerging technologies and hybrid memories as part of the main memory system. And then we'll finish this and start quality of service or memory interference today. So remember we were talking about, what we did was we covered some emerging technologies which are promising to potentially replace DRAM or augment DRAM. We talked especially about phase change memory, and we talked about what happens if you actually took DRAM out of the system and put phase change memory with some parameters into the system. That's probably not a good idea currently, at least. Even if you re-architect the phase change memory chips, it may not be a good idea. So we were looking at hybrid memory systems which look like this, right? Some part of your memory system consists of a small amount of DRAM, and a large part of your memory system consists of a large amount of some of these emerging technologies, phase change memory. And actually some of the ideas that we will discuss are applicable to not emerging technologies as well. You could think of the system as maybe a fast DRAM versus much slower DRAM, right? Maybe you can manufacture much slower DRAM at lower cost going forward into the future. So these techniques, keep in mind when you think about these techniques that this doesn't have to be an emerging memory technology. It can be an existing technology that's manufactured in a very different way than today to minimize its costs and maximize its potential scalable. So it's good to think about systems that way. Actually, if you think about systems that way, this could be maybe stacked DRAM and maybe DRAM itself, and maybe you can have slower DRAM later on somewhere else in the hierarchy. Okay, basically we were talking about how the hardware and software manage data allocation and movement to achieve the best of multiple technologies. And this is the slide I left you with. Right? One option was to use DRAM as a cache for phase change memory, and we covered there are good reasons for it. So we're going to look at how can we manage this cache. There were three issues. First, what data should be placed in DRAM versus kept in phase change memory? What is the granularity of data movement? And how do you design a low-cost hardware-managed cache? And again, these issues exist in hybrid technologies that do not necessarily have phase change memory in them. So two idea directions we'll explore: locality-aware data placement and cheap tag stores and dynamic granularity. But before that, let me talk about a paper that actually introduced hybrid memories. This was Moinuddin Qureshi's paper at IBM. He's at Georgia Tech now, but I would recommend this paper also. It'll be part of your readings if I can access the internet from here somehow. At some point I'll be able to do that. But this is a figure from him. But the goal was very similar, to achieve the best of both DRAM and phase change memory, non-volatile memory. And the idea was to minimize the amount of DRAM without sacrificing performance or endurance. We saw that both of these were problems, right? If you actually don't have DRAM in the system, just have phase change memory, you sacrifice both performance as well as endurance. In fact, endurance is a functionality problem. You don't want your memory to be destroyed. We'll get to that toward the end of the lecture. So the idea is to use a DRAM cache to tolerate phase change memory latency and write bandwidth issues, because write bandwidth is actually low to phase change memory, as we've seen earlier. And phase change memory is used as main memory to provide large capacity at good cost and power. So you have a small amount of DRAM buffer which is used as a cache, so you need to have a tag store, which we will discuss. And there's some write buffer also, such that you can actually coalesce the writes that go into phase change memory. So this is what your memory system looks like. It used to be only DRAM. So it's of course very important to manage this DRAM buffer that's sitting in front of your phase change memory. And the idea is to minimize the writes that go into phase change memory, right? We discussed this yesterday. And there are several techniques that were employed in this paper, and we'll look at the benefit of it in the end. One is lazy writes. For example, when you bring a page from the disk, you install it into the DRAM. You don't write it into the phase change memory. Only when the page is evicted, you write the dirty parts of that page, dirty lines from that DRAM page into the phase change memory. So you need to have some management to figure out where the lines are if you have a system like this. And you have actually page bypass if you have pages with poor reuse. So you can keep some counters in this tag store, some metadata in this tag store about each page, and figure out the pages that do not have a lot of reuse. And if a page doesn't have a lot of reuse, maybe you don't write it back to main memory after that. You write it directly to the disk, right, if it's dirty. So that's the idea. If you do these techniques, you can actually get rid of a lot of the writes that happen to phase change memory. And these are some results from Moyne's paper. Basically, this is, he did a system-level simulation of a 16-core system, 8 gigabyte DRAM with some number of cycles to access it, hard disk drive, and with flash, and there's a flash hit rate as well. So these are long-running workloads. Some of them are database applications. And the assumption is that phase change memory is 4 times denser, but also 4 times slower than DRAM. And this could be a reasonable assumption going into the future. Maybe it's not denser today, maybe it's not low cost today, but scalability is high. So it's always good to do these studies looking forward into the future. Otherwise, you will never get to the future, right? Okay, so DRAM block size was assumed to be phase change memory page size. And if you look at this, there are a bunch of applications. This is the geometric mean of the execution time across those applications. And it's normalized to the baseline DRAM system, which has 8 gigabytes. And this blue one is a 32 gigabyte phase change memory system. So this actually takes into account the effect of having larger memory. So this actually simulates the page fault. The previous result that I showed you didn't simulate the page fault. We assumed that the sizes of DRAM and phase change memory were the same. But here, if you actually take into account page faults, and if you assume that an 8 gigabyte DRAM occupies the same amount of area as 32 gigabyte phase change memory, then actually using phase change memory is a win. Right? Significant win. You actually reduce the execution time by 2x. You improve performance by 2x. And the comparison point, a 32 gigabyte DRAM, if you look at it, this is actually consistent with the results that I showed you in our paper. You actually lose significant performance at the same memory capacity. DRAM is still much better than phase change memory at the same memory capacity. Now, if you employ hybrid memory, you kind of get the best of both worlds. In fact, better than the best of both worlds. You have a 32 gigabyte phase change memory plus 1 gigabyte of DRAM. You could argue that this is not a perfectly fair comparison, and you'd be right, because you have 33 gigabytes of memory, but that's okay. 1 gigabyte of additional DRAM perhaps doesn't help that much. And it'll be worse for power. So if you look at this, what you get is you actually approximate the performance of 32 gigabyte DRAM. You're very close in terms of execution time. So that's the idea. You get very close in terms of execution time to a fully DRAM system with a much lower cost system. And the hope is that this is much lower cost, right? 32 gigabyte PCM plus 1 gigabyte DRAM. And if you look at energy efficiency, basically the conclusion is that a hybrid memory performs similarly to similar sized DRAM, but you get significant power and energy savings with the PCM DRAM hybrid. This is the power results. This is 8 gigabyte DRAM normalized to that. Higher is actually worse. But if you look at 32 gigabyte DRAM, that's a lot of power. It has a lot of leakage and refresh power. And a hybrid memory is in between 8 gigabyte DRAM and 32 gigabyte DRAM. And it actually has even a little bit more memory. And energy is better also. Energy is the lowest with hybrid memory, and energy delay is the lowest with hybrid memory. So that's the idea. If you can actually have this large capacity memory system, which is enabled by the density and the scalability of phase change memory, you get better energy, better power, and on-par performance with DRAM. So I like these simulations because these do take into account those real system effects like page faults as well. We did not take that into account in the previous paper because we want it to be more aggressive. But this is actually perhaps a more realistic view of the system. Okay, any questions? So I would recommend actually you to read both our paper as well as this paper. They were presented at the same conference in the same session, almost at the same time, back to back. I guess there's some energy in the world that makes people work on similar topics and come up with some similar ideas at the same time. Okay, so let's take a look at, can we actually do better with these results? So we have, let's assume that we have these baselines with hybrid memory systems, but can we do something better? So I'll talk about taking into account locality. I'll do these very quickly actually, and I'll talk about how to design efficient DRAM caches. I won't go into too much detail, but hopefully you'll be able to develop more ideas beyond this. So, hybrid memory, the key question is how do you place data between the heterogeneous memory devices? Let's assume we employ everything that we've discussed so far. One thing that doesn't take into account is the locality. And we'll try to take into account the idea of row buffers, and you know that very well today. If you look at DRAM and phase change memory, they have things in common. They have banks, but they also have row buffers. These row buffers you need to access data from. And the observation is that, well, you already know this, but basically if you get a miss in the row buffer, you need to access the cell array, right? And then array access is long, both in DRAM and phase change memory. But it's much longer in phase change memory, right? Especially if you want to do a write. But if you want to do a read, that array access is long. Okay. If you get a hit in the row buffer, you don't need to access the array, which means that the access is fast. The observation is that, well, we know this basically, we talked about it. But the observation is that row buffers exist both in DRAM and phase change memory. And they're actually very similar to each other, or they can be architected to be very similar, because after you get the data into the row buffer, it's essentially an SRAM-like circuit, right? Basically, there's no reason they have to be different significantly. Which means that the row hit latency is similar in DRAM and phase change memory. And row miss latency, on the other hand, is very different. It's small in DRAM, relatively, but it's much larger in phase change memory. It's 4 times larger for reads, 12 times, or maybe even greater than 12 times larger for writes. So the idea is very simple once we make this observation. We'd like to identify the data that are likely to miss in the row buffer, that have low row buffer locality, and place them into DRAM because the miss penalty is smaller in DRAM. If the data has great low buffer locality, it really doesn't matter where you place that data, because you'll get the same latency and same bandwidth because you'll be accessing the row buffers. But it makes sense to place that into phase change memory actually, right? Because DRAM is precious. You don't want to use DRAM space for data that you will access with the same latency and bandwidth in phase change memory. So that's the idea. Identify the data that has good row buffer locality or low row buffer locality and is reused many times and put that into DRAM. And everything else, put that into phase change memory. That's a simple observation that takes into account row buffer locality. I'll probably go over this very quickly, but this is just an animation that shows, let's say you have 2 rows with low row buffer locality that frequently miss in the row buffer, and 2 rows with high row buffer locality that frequently hit in the row buffer. Let's take a look at 2 policies. One is locality unaware, that's the state of the art, and one is locality aware. If you have a locality unaware policy, you could place the rows that have high row buffer locality in DRAM and the other rows that cause a lot of row conflicts in phase change memory. And what would happen in this case? Let's assume you have this access pattern. You can actually construct different access patterns, but you'll get similar benefits in many access patterns. What would happen is, DRAM, you'll get a lot of row hits, and you get some row conflicts the first time you access a row. On the other hand, with PCM, you get all row conflicts, which means that you need to access that slow array over and over. So the stall time, basically how long the processor waits for all of these requests in total, in aggregate, is 6 phase change memory device accesses, because you're parallelizing these 2, assuming that you have the hybrid memory that you can access in parallel. But if you had a policy that's aware of locality, somehow you figured out that these rows have bad locality, they cause row conflicts, but they're also reused somehow, and you place them into DRAM, and you could do this in hardware, you could do this in system software. I'll briefly talk about a technique in hardware where you can identify, and you could use the ideas to feed the system software also. But somebody allocates these rows into DRAM, and somebody also allocates these rows that have higher buffer locality into phase change memory. And if you do this, the same timeline turns into this. Now DRAM has these rows that cause a lot of row conflicts, but row conflict latency is much shorter in DRAM. So this is what you get. And phase change memory has these rows that have high row buffer hit rates, and it's okay to place those over in phase change memory because you're not accessing the array that much. As a result, your stall time in this case is 6 DRAM device accesses as opposed to 6 phase change memory device accesses for all of these requests in aggregate. So you save a bunch of cycles. That's the idea. That's the idea of exploiting this row buffer and locality that exists in both devices. Make sense? Okay. So how do you actually do this? I'll not go into too much detail of this, but basically you can have simple counters in the memory controller that count row buffer misses and use that as an indicator of row buffer locality. Basically, for a small group of rows, you count how many misses you've seen for those rows. And if the misses for a row go above a threshold, then what you do is the memory controller takes that row and caches into DRAM. And this is actually a good indicator of both locality as well as frequency of use. Because if you actually have a lot of misses greater than some threshold, that means you're frequently using that row. Right? And the hope is that that past behavior is a good indicator of the future behavior. And there's another thing that is discussed in the paper. Basically, you dynamically adjust this threshold, right? Usually, whenever you have a threshold, it's dangerous, and a single threshold is not robust. If you can adjust this threshold to workload and system characteristics to figure out what threshold value is doing better. And you can read the paper for that. Basically, sometimes you would like to cache things right away, sometimes you'd like to wait for a while, depending on your working set size, for example. Right? If your working set size is huge, and if you cache everything right away, then you'd be trashing your DRAM cache. And you don't want to do that. That's why it makes sense to adapt this threshold dynamically to the workload behavior. Okay? So how do you implement this? Basically, you have a statistics store in the memory controller that looks like a cache. You have an input that's a row address, and the output is a row buffer miscount. And you can actually make this relatively small by sampling the rows. Basically, this is the size that we use. A small store performs as well as a large store. Basically, you don't lose a lot of information. Of course, you need to update this store such that you don't have stale information. But if you have a small store, that updates itself automatically. So what's the benefit of this? Let's take a look at it quickly. Actually, I would encourage you, if you're interested in this area, I would encourage you to think about how to do the simulations in this area also, because you need to simulate large memory systems. And even this is not large for my taste, in fact. You have 1 gigabyte DRAM and 16 gigabyte PCM, and a 4 gigabyte migration granularity. And my students actually have a bunch of different workloads, some database workloads and web server and video, other workloads, mixes of that emulate cloud-like workloads. And there are a bunch of metrics. But let's take a look at the comparison points. Conventional LRU caching is one comparison point. If you actually do least recently used replacements in DRAM, it's a terrible idea in hybrid memory because you're moving pages that are very large. And it turns out this doesn't work very well. That's why actually in the previous paper that we discussed, they don't use LRU caching also. So there's one proposal, this was in HPCA 2010. Basically the idea is to do caching based on the access frequency of different pages. Basically, it keeps track of DRAM rows, and if the accesses are greater than some threshold, it's cached in DRAM. And this was proposed for large DRAM caches, not for hybrid memories actually. But this is not aware of locality, so this is a good comparison point for us. It does frequency-based caching, but it's not aware of locality. And you can actually use our adaptation mechanism to adapt it dynamically, adapt that threshold dynamically. And the comparison point is row buffer locality-aware caching and the dynamic version of it. Dynamic version actually adaptively changes the threshold. So I'll just focus on this dynamic version and compare it to this frequency-based caching. So I'm assuming frequency-based caching is the baseline because LRU is a terrible strategy for this kind of cache at least. And if you look at this, taking into account locality decisions actually improves performance significantly on these types of workloads, both server and cloud workloads. And the reasons, there are actually several reasons. One is, we're increasing row buffer locality because the low row buffer locality data is in DRAM now. And the second thing is the memory bandwidth consumption is reduced because the caching criteria is more strict. Only things that have good locality bad locality are cached in DRAM. And finally, there's more balanced memory request load between DRAM and PCM. If you actually caching everything in DRAM and accessing everything from DRAM is not a good idea because you're not utilizing the phase-change memory bandwidth very well in that case. And remember, this may be a good option if you have a disk plus memory, because disk bandwidth is extremely low, right? It's impossibly low. Using that in parallel with DRAM may not make sense. Whereas with something that's much closer to DRAM in terms of both bandwidth and latency, you don't want to waste that bandwidth. You'd like to balance, at least somewhat reasonably, the load that goes to both memories. So I think it's good to think about how these memories change the landscape of storage and memory compared to the disk systems that we have today. This makes sense only because phase-change memory latencies are much closer to DRAM. If you try this in disks, I guarantee you that you won't get much benefit because it's so impossibly fun. Okay, so the average memory latency also reduces because you get better row buffer locality, in fact. And also for the other reasons, the contention reduces. And energy efficiency also improves. Again, for any different reasons, but you can read the paper for the reasons. Well, I guess one is you increase performance, that's one of the reasons why energy efficiency improves, and you have reduced data movements between these memories. And that data movement is actually expensive. You would like to minimize that. So I guess I'll do this comparison too. So this is again a comparison that assumes the same amount of DRAM and phase change memory, if you look at this. This is a 16 gigabyte phase change memory system, that's the normalized performance. This is a 16 gigabyte DRAM system, that's the normalized performance. So there is a gap that's very similar to what we've seen before. And this is where this dynamic policy actually gets you. Somewhere in the middle. Assuming you have the same amount of memory. So hopefully, for the same cost, you'll get much more phase change memory. So this, the trade-off is on the side of the phase change memory. So the hybrid memory system actually is in between, assuming the same amount of memory. It's in between the phase change memory and DRAM. Any questions? No. Okay.
What about the thing that you said about the phase change memory? Is that solve the probability that the one bit flips or the results flips? What related to the bit flips or should we proposing?
How reliable are they? Is that the question? Yeah. Well, that's a research topic also, actually. How reliable reliably you can store data in any of these emerging technologies is a research topic.
So they do not need a refreshing mechanism, right? Because they are phase change.
Yes. Yes, there is no need for refresh because they're not leaking data, but there are other potential reliability or error mechanisms that are present in these memories. For example, wear out is definitely a reliability issue, right? You can actually extend the lifetime with better management. There's also something called the resistance drift. The resistance of the material actually drifts. And it's not clear what the effect of that is in phase change memory today. There are some papers related to it, but we can talk about it. I can actually talk to you offline about some of the papers. So there are a lot of interesting issues in emerging technologies that need to be handled still. But remember, these issues also will show up in DRAM. Right? DRAM, as DRAM scales down, it'll become more error prone. And I think, for example, if you look at flash memory systems today, the flash controllers do a lot of management of error. Right? There's a lot of error correction. It's increasing going into the future. I believe going into the future, DRAM will look increasingly like that also because we'll have to somehow tolerate the errors that we get in the smaller technology nodes. So if you think about memory systems, flash memory, how many of you are familiar with flash memory? Okay, some of you. Everybody else knows? You all use flash memories, by the way, with the USB drives and actually in all of your laptops today probably. I don't know if there's any laptop manufacturer that doesn't use an SSD today because it's such a big win. But basically, flash memory is a storage device today and has a controller. And that whenever you read data, you never get correct data from flash memory. That never is probably a strong word, but based on the experiments that we've done, it's very unlikely that you're going to get correct data, the data that you wrote. So there's a lot of error correction codes that happen in flash memory, and these are increasing. It's becoming very difficult to correct these errors. So what flash memories have is they have an acceptable bit error rate, which means that this amount of error is tolerable. And you're expecting to get those errors. And there's error correction that's applied on top of that bit error rate, and you still have an acceptable bit error rate. Whereas in DRAM, our industry has been so far, DRAM is perfect memory, right? There shouldn't be any errors. That's the assumption. That's going to change into the future. That's not true today also, actually. You do get a lot of soft errors in DRAM, right? And you do not know. That's part of the problem. That's part of the good thing. You could not know there are no errors, right? But actually, that's going to increase into the future. And I believe increasingly, the interface of DRAM will look maybe more like flash, maybe not to that extreme, but will have some acceptable bit error rates, and the manufacturers will be able to scale down the technology by saying that, okay, we cannot correct all the errors, but we're going to give you an acceptable bit error rate, and we're going to guarantee operation within that error rate. So that enables better scaling of any memory technology. So in the end, fundamentally, all memory is really similar. And if you want to scale memory, you may need to go into that direction. But basically, all technologies will have these reliability issues that need to be solved. Okay, so let me summarize and go on to this other direction. Basically, different memory technologies have different strengths, and we've seen that. A hybrid memory system aims for best of both. And one of the key problems is how to place data between these heterogeneous memory devices. And the latest observation that I've discussed is phase change memory array access latency is higher than DRAM's. Actually, this was an earlier observation. But the peripheral circuit access latencies are similar. The row buffer access latencies are very similar. The key idea, if you actually figure out which rows have good locality or bad locality, you can use that as a key criterion for data placement. And you can cache to DRAM the rows with low row buffer locality and high reuse. And this improves both performance and energy efficiency over the state-of-the-art caching policies. So you would like to do locality-aware placement. And my feeling is there's a lot more small things that you can do to enable data placement this way, better data placement. And once you have this information, you can actually expose it to the system software such that the system software does even better management. We did not explore this, but it can be explored. So let me switch gears and talk briefly about how do you actually architect efficient caches. And this is another problem if you have a hybrid memory system and you would like to use one technology as a cache for the other one. And the problem is, if you want to build any kind of large cache, it requires large metadata. Right? Think about, I guess I'll pick some number, 4 gigabyte cache. And your cache blocks are 64 bytes. And assume your tag size is 4 bytes. Now we'll have to do the calculation. 4 gigabyte cache, 64 byte cache blocks, that's 2 to the, I guess people are waking up, 32 divided by 2 to the 6, 2 to the 26, right? That's 2 to the 26 blocks stored in the cache. And if you require 4 bytes metadata for each block, that's a lot of metadata, right? 2 to the 26 times 4 is 2 to the 28. That's 256 megabytes. Am I wrong? Something like that. 2 to the 28. You don't want a tag store that's that big, right? For a 4 gigabyte memory. So we don't want that space. We'd like to make it scalable. One option is actually having the memory controller, put this in the memory controller, right? But that's not a good idea. That consumes a lot of power that you would probably save from a hybrid memory system. And also that is not scalable. If you want to add more memory into the system, then you'd like to increase the size of the tag store also. Right? So the key question is, how do you actually design this tag store? And I'll briefly give you some ideas, but this is, I think, going forward, still an interesting problem. And this is actually a very industry relevant problem. This needs to be done, yes.
You have such an architecture, small lifetime.
That's a good question. Yes, you could argue that way. I gave you the worst case potential. Maybe you use larger line size, but the problem still remains, right? Maybe it's not 2 to the 28 bytes, but maybe it's 2 to the 22 bytes, which is still large. Okay? But that's a good point. But I'll show you the benefits of using dynamic granularity also. And that's one of the reasons why you would like to use a line size that's small enough such that you can adapt how much data you fetch. And that actually provides a lot of benefits. I'll show you some results. Okay, basically the problem is when you get a load, you would like to determine whether it's whether you service this from DRAM or phase change memory, and you need to consult some metadata, and that metadata says X is in DRAM or X is in PCM, and you access X. If it's a hit in the tag store, you access X from DRAM. If it's a miss in tag store, you do something else. So how do you actually design this metadata store more scalably? This is one idea that we've looked at, and others are looking at this idea also. Basically, the first idea is not rocket science, right? It's basically store the tags in the same row as data in DRAM. Actually, this is the first idea that you would perhaps develop that were proposed before is allocate a portion of your DRAM as a tag store. And that's actually not a good performing idea, and I'll show you some results. It's better to put the cache blocks and the tag store in the same DRAM row because you exploit the locality that way. Because if you hit, you're going to access the cache block in the same row, right? So you get a row buffer hit. That's the idea. Data and metadata can be accessed together. And this is a scalable way of building the tag store because as you increase the size of your DRAM, your tag store also increases. The benefit is there's no on-chip tag storage overhead because tags are all in DRAM. There are downsides, of course. One is caching is determined only after DRAM access, right? You have to access this row first and figure out hit or miss. And the cache it requires 2 DRAM accesses, whereas you really would like the cache it to be very quick. Cache it meaning a DRAM cache it. So the second idea tries to accelerate that cache it. Basically, we'd like to cache the tags themselves in SRAM, some on-chip SRAM structure. The first idea was to store all metadata in DRAM. If we cache some of that metadata in frequently if we cache the frequently accessed metadata in on-chip SRAM, then perhaps we can keep that SRAM size small. We don't need to put the entire tag store in SRAM. And actually, you can develop some more ideas going into, you can prefetch. If you have good locality, you can prefetch the tags from DRAM into the SRAM from the on-chip cache. You can basically orchestrate the tag movement. I know this is all adding complexity into the system, but this is what you need if you need a large tag store. Or maybe your idea would be much better than this. Hopefully. Okay, the last thing which is orthogonal is, I guess partially answers your question maybe. We would like to have dynamic data transfer granularity. Some applications benefit from caching more data. They have good spatial locality. In that case, you may want large blocks. But many other applications do not. They just want actually a word even. You don't even want a cache block. So in that case, large granularity wastes bandwidth and reduces cache utilization. And remember, DRAM space is very, very precious in a hybrid memory system. And the third idea is to have a simple dynamic caching granularity policy. I'm not going to go into this in detail. You can read the paper. The paper is actually only 4 pages. I'll give you the pointer. But basically, we have a cost-benefit analysis to determine the best DRAM cache block size. And other people have used similar mechanisms. Basically, you have a bunch of different granularities with which you can cache data, and you dedicate some portions of your cache to use that granularity. This is basically sampling. It's the idea called set sampling. And some sets follow, let's say, 64 bytes caching, some sets follow 1 kilobyte caching, some sets follow 4 kilobyte caching granularity of data. And you figure out which one has a good hit rate. And then you pick the caching granularity that's the best. This is the idea. The idea is called set sampling. We had actually introduced it in the ISCA 2006 paper. And I'm not going to that in detail, but that's what you do. It's not a great mechanism. It doesn't scale very well, but if you have few number of the granularities, you can pick the best granularity. And it works. It's relatively simple. So basically, well, I guess I already given you the idea. Group main memory sets into rows. Some row sets follow a fixed caching granularity. The rest of main memory follows the best granularity. And you have some mechanism to determine what's the best granularity. It could be miss rate, it could be stall time. And this is performed over time. Basically, in this quantum, you figure out the best granularity. In the next quantum, time quantum, you use that granularity. In the next time quantum, you figure out the best one, and the next time quantum, you use that one. So let's assume that you do that. That's the third idea over here. So I'm going to skip this because this is basically showing how the tag accesses are done. Basically, this is tag in memory buffer. This is the SRAM cache, tag cache. If the tag is cached, there's no need to access DRAM twice, right? Which means cache it is determined quickly. Okay. I guess I wanted to skip the next one. Basically, you would like to keep the tags that you're accessing cached in on chip. You don't want to access DRAM for those. Okay, I'm going to skip this one. You can animate it on your own. All of these slides will be online. And actually, some of them are online. Okay, a little bit about the performance of this. So let's take a look at the performance. These are, again, you can read this in the paper and the slides. But basically, if you can have an all SRAM system, and this is actually a small simulation. We have larger simulations now. We're going to compare 4 different systems. One is all SRAM. Basically, all tags are in in on chip. This is expensive. In this case, it was 8 megabytes, but it can actually be much bigger. The second is region store, where a portion of the DRAM is dedicated for tags. The third one is the tags are in the same row as in data, tags in memory. And the fourth one is you add a small SRAM cache to cache the tags themselves. And this can be much smaller than the entire tags that you have to put in SRAM. Let's take a look at the performance of this. So we call this the metadata actually, because it's not only tags, right? You may want to keep information about different rows in memory as well. That's why it's metadata. It's something related to data. So this is the SRAM. This is the ideal case where you have all the tags on chip, and this is the best performance. You cannot do better than this, at least with these mechanisms. If you actually store the tags in part of DRAM, you lose a lot of performance because you need to do DRAM accesses, and they're all robot for confidence, right, even if you get a cache. If you store the tags in the same row as with the data, then you get better performance. And this makes sense, right, because you get better row locality. Now, if you actually cache some of the tags on chip, you get better performance than that also. But we're still not as good as fully on-chip SRAM tag store. Make sense? So we're trying to approximate that SRAM tag store. You get reasonably close, but not perfect. And the reason is you don't always hit in this cache of the tag store. Okay, so if you actually add dynamic granularity on top of this, and I don't believe this is the best mechanism, probably you can come up with even better mechanisms than this, you can get 10% additional performance. So if you change the granularity dynamically, you get much better performance because you reduce the channel contention and improve spatial locality in the caches. And this comes within 6% of an ideal SRAM cache. Now this is not a fair comparison again, because you could actually do dynamic granularity on top of the SRAM tag store. And you see that this also improves if you do that. But this is another area that's very interesting actually, going forward. Can you design a very large cache and get the performance of an ideal tag store, where ideal tag store is purely hardware, large tag store that's implemented in SRAM? I do not think we're there yet. Okay, energy efficiency also actually improves with these mechanisms. As you look at this, you improve energy efficiency because you reduce the accesses that go into DRAM with all of these techniques, and you reduce channel contention, especially with the dynamic granularity. The biggest benefit comes from the dynamic granularity of caching. Okay, so if you'd like to look at more on the large DRAM cache design, this is the paper that I described. But this is also another paper that was published in Micro last year that comes to similar conclusions in many of these. Okay, any questions on this? I know I've gone really fast, but that's part of the purpose. No? Okay. So I believe this is a very interesting research area going forward, enabling and exploiting these. I call it NVM here, but they don't necessarily have to be non-volatile memory, but they happen to be non-volatile. But emerging technologies in memory. There are many issues and ideas from the technology layer to the algorithms layer, basically all the way from maybe even problem formulation down to devices. How do we tolerate errors? You mentioned that. How do we enable secure operation? I'll briefly discuss that. I won't have any answers, but I'll give you some potential research directions. How do you tolerate performance and power shortcomings, and how do you minimize cost? There's also exploiting emerging technologies. How do you actually exploit non-volatility in main memory? Can you actually merge memory and storage? How do you minimize energy consumption? And how do you potentially exploit non-volatile memory on chip? And I believe these are all very interesting research questions, some of which are being examined, but some of which are open. I'll give you three security challenges of these memories that as I see them. I'm sure there are a lot more. One is limited endurance. Right? Limited endurance actually is a security challenge because you can have one application destroying the memory while another application is not even using it. Right? And when it needs to use it, too bad. You don't have any memory left. So this is wear-out attacks, and it's interesting to look at this, I think. The second is non-volatility actually can be a curse as well, right? We've been used to our memories being volatile, and we relied on that so that people cannot steal information, right? If you lose your cell phone, the memory is wiped out, right? But whereas if you have a non-volatile memory, data persists in memory even after power down. So somebody can easily retrieve privileged or private information. And this is actually a real problem, and how do you solve that is an interesting question. And actually, you can have information leakage from these memories also, because you can store multiple bits per cell. I won't go into this in detail, but you can think about that. So route attack, people have actually looked at this problem. Perhaps you can better architect memory chips to absorb writes. You can do better hybrid memory system management. You can perhaps do online detection of these attacks. The problem is, what is an attack and what is a real program, right? That's always a problem. You can have an extremely write-infested program that looks like an attack, right? You may not want to deny that. But I think providing guarantees here is very important. Non-volatility, people have looked at efficient encryption, decryption of all main memory. It may be extremely expensive. And better hybrid memory system management is again an interesting direction here. And side channel attacks, I think I'll let you figure that out, perhaps. How do you hide side channel information is a general security problem in systems where you have shared resources. Right? Okay. But it's actually, this part is interesting because people have demonstrated attacks with DRAM. So what they've done is, this was a paper by Halderman in Unix Security in 2008, and I think they called it the cold boot attacks on DRAM, right? Memory remnants attacks. And the idea was, after you power down the system, you take the memory and make it really cold, and that preserves the data because that actually lengthens the amount of time the DRAM stores. Remember, DRAM is volatile, but remember that curve. Some cells actually can keep data even at high temperatures for tens of seconds or hundreds of seconds. So if you actually make those cells keep data even for longer by making it extremely cold, you can actually retrieve keys that are private from others. And I encourage you to read that paper, Unix Security 2008, John Halderman and others. It's called cold boot attacks, and they show that you can reconstruct images from DRAM that were just persisting there even after the system is powered down. So ideally, we would like to make DRAM non-volatile also. That's what we're trying to do with the refresh issues, right? But that is a downside. Then the question is, how do you manage that? Okay, let me conclude this part of the second topic, and I'll give you some pointers after that. Basically, we've looked at main memory scaling from a different perspective in this case, and these problems are critical bottleneck for system performance, efficiency, and usability, I believe. The first solution we've examined in the first topic was tolerating DRAM, and this was the conclusion of the second topic, how do we enable emerging memory technologies. And we looked at two main directions, replacing DRAM completely with non-volatile memory by architecting non-volatile memory chips well, phase-change memory chips in this case. This may not be a very viable option, but perhaps a more viable option is hybrid memory systems with automatic data management. And actually, I think fully automatic is perhaps not the right answer, because if the applications know where to place data, that might be a good idea to actually use those hints to put the data. I believe this is an exciting topic with many other solution directions and ideas. And in all of this, hardware, software, and device cooperation is essential. In fact, it'd be good to figure out what are the requirements that we want from these devices and influence the development of these devices going forward. And you would like to design memory, controller, software together, and maybe even storage. And this is an exciting direction also. How do you actually have persistent memory and storage together, and how do you manage them together, given that you have a huge non-volatile memory today? And again, I think it's not only hardware, it has to be hardware-software cooperative, because software has a lot of information, especially when you go into persistence. What should persist and what should not persist is a decision that needs to be made by the software. So I'll point you to two things. This is a paper that I presented at ISCA this year, the READ workshop. It talks about the potential opportunities in merging memory and storage. And it's a short paper also, it's 6 pages. It's more like a research overview direction. What are the benefits of having non-volatile memory and storage together and managing them with a single interface? I briefly talked about this yesterday. But given these emerging technologies, we should really rethink the way we design the memory and storage system together. And I'd be happy to talk about this going forward. And something we did not really talk about, flash memory scaling. There's a lot of interesting problems over here, and this gives you an overview. This was published in Intel Technology Journal this year. And if you're interested in that, there are a lot of interesting issues in flash memory scaling as well.